So if you have a composite function, you want to find the limit, then as long as the components are all continuous, it's relatively easy. I'll state the theorem and then we'll do a couple of examples. So let's say given functions f of x and g of x. If, let's say if the limit as x goes to a of g of x is b, okay, two-side limit, and f is continuous at b, then the limit as x goes to a of f of g of x equals f of the limit of x, or as x goes to a of g of x, which then equals f of b. Okay, so if you have two functions, well, let's phrase it this way. If you have a composite function whose limit you want to find, and the outside function is continuous at the limit of the inside function, then you can just go ahead and move that limit inside f, and that will work fine. If f is not continuous, well, then it depends, and you're going to have to do like one-sided limits and check very carefully. But if f is continuous, just go ahead and swap it. It's kind of like, it's sort of like saying, oh, we're going to plug this in, right? You know, if your function is continuous, you just plug in and you get the right result. It's akin to that. It's similar. The f is not going to cause any problems with trying to find the limit as long as f is continuous at the limit value for the inside function. Okay, so let's do an example of that. Let's say I have, let's say we have the limit as x goes to, well, let's see, what do we want to do? Let's say 1/2 of, let's say, cosine of the square root of 1 minus x squared. Okay, so I can take this limit and move it inside the cosine function as long as that doesn't cause me domain problems or continuity problems later. As long as cosine is continuous at the result, like after I move the limit inside and I get some numerical result here, as long as cosine is continuous at that result, then it was okay to do that. So you kind of have to just start doing it, and then if you realize, oh, this isn't working, then that means that the first step was improper. It wasn't going to work, but of course you don't know that until you get started. Kind of like when we go to we have a limit and we just plug in the number to see if we get a result, knowing, well, we might get 0 over 0. And in that case, that means that it was not proper to plug in to begin with, right? It doesn't work, but you don't know that until you try, right? So it's kind of like that. You just try it, and then if you run into a problem, you have to backtrack. And if you don't run into a problem, then that's it. You just get the result. So I'm going to say that this is equal to cosine, because I know cosine is continuous on its entire domain, right? Cosine graph is a sinusoidal graph. There are no jump discontinuities or anything, so it's continuous for any input. So I'm pretty confident this is going to work out fine. I'm not worried about cosine, I mean, the domain is all real numbers, and it's continuous on its entire domain, so cosine isn't going to cause a problem. The only thing that might cause a problem is if we run into a problem later. So limit as x goes to 1/2 of the square root of 1 minus x squared. Now, power functions you have to be careful with. These are continuous on their domains, except we talked about, I think 2 days ago on Monday, when you look for the limit of a radical function, a root function, where you're right on the edge of the domain, then it's questionable, and different books will call it different ways. We'll say the limit exists. We wouldn't require the square root function to be continuous, to be left continuous at 0, right? this, just to summarize what we talked about previously, if you take the square root function, which looks like that, right? You wouldn't ask for being continuous. I'm sorry, having a left limit. Like you wouldn't even bother with that. So let's not worry about it. The textbook, I didn't notice until today, actually goes into more detail on that. So the textbook will say that this function is right continuous at the endpoint of the domain. At 0, the function is right continuous. Let's not worry about that too much. We'll just worry about continuity in general. We don't need to talk about left and right continuity. The That's kind of what we were doing here, so to speak, but none of the homework problems use that terminology, so I'm not going to worry about it. But if you want to read in the textbook, it does go into a little bit more detail on left continuity and right continuity. So let's make a note for people. Let's make a note here. So when I look at this later, note, the text gives more detail on left and right continuity. Okay. So when I consider, oh, well, can this limit move inside the root? Well, is this root function a continuous function? Well, as long as the input is a positive, as long as the inside part turns out to be a positive number, yeah. Again, the graph looks like this, right? It's a smooth curve. You can draw it in one motion. It's continuous. So as long as we don't end up with like a root of a negative, which causing a domain problem, yeah, that should work fine. So this is the cosine of, of the square root of the limit as x goes to 1/2 of 1 minus x squared, right? So now we can say, well, can we plug in now? Well, this is a polynomial, 1 minus x squared. Of course, you just plug in. It'll work fine. So this equals cosine of the square root of 1 minus 1/2 squared, which is not exactly a pretty number, but that's the result. Now we might want to consider, you can write a thing. I can write cosine inverse of 17 if I want, but that's not defined. The cosine inverse doesn't accept 17 as an input. I can write it down, doesn't mean it works. So we should check and make sure that this actually works. Don't just write it and move on from there. I need to make sure I don't run into any domain issues. So this is cosine of, well, let's start from here. 1/2 squared is 1/4, and 1 minus that would be 3/4, right? 3/4. So this is the square root 3/4, right? Or if I want cosine of root 3/2. And you don't usually see root 3/2 as an input for cosine. You typically would expect it as a common output for cosine, right? Cosine of pi over 6 is root 3/2. But cosine accepts any real numbers as an input, so yeah, that checks out. So that's the result. That's the limit. And of course, I'm writing this step by step, one at a time, but you can look at this and go, well, cosine is a continuous function, and the square root function is a continuous function, and you can go from this step to that step in one go. You don't have to write them out separately. I'm just emphasizing the use of the property. As long as the functions are all continuous, you just plug it in and it'll work fine, okay? Unless you have a domain issue, of course. So the functions have to be continuous at the inputs that they receive. And of course, cosine is continuous for all real numbers, but the square root function is not. I think I want to do one more. Let me find one.
Hey,
Yeah,
Professor, I have a question about the example we just went through.
sure.
Um, I'm looking at cosine of what's inside of what's called, I guess, the container,
Yeah,
and I didn't realize that we could I'm trying to understand. I don't know which specific limit law allows us to push the limit into the container.
This one.
Right.
Yeah, it's the one it's a new one. It's not a one we've had for a while.
Okay.
Yeah, so kind of like how whenever you have a continuous function, continuous means that the function being continuous at a point means that the function is defined at that point, the function has a two-sided limit at that point, and the limit and the function agree at that point, right? That's what continuous means. And our list of continuous functions, so far at least, is polynomials, rationals, continuous at points in their domain, exponentials, logarithms, all the trig functions. They're all continuous at points in their domain. They're not continuous at points outside their domain. So there's an exception, which we'll do in a second. Um, so we have to be careful that we are, as long as a function is continuous at the points that it's receiving within that problem, then you just plug things in and you don't have to worry about problems. Basically, you start by not worrying about it, you just plug them in, and then you simplify the expression. And then if you get something like, oh, I have like cosine inverse of 17, that doesn't work, right? But you would start by, as long as the functions appear to be continuous generally, you just have to know, oh, I know that their domain is not all real numbers. You just plug in, and then if you don't run into a problem, then you don't have a problem.